used to be a show on TV called Are You Smarter Than a Fifth Grader? It was popular, but it was also a disturbing reminder of how much information we forget over the course of our lifetime, especially given what a fifth grader knows. Well, I'm afraid I have more disturbing news for you. If you've ever tried to visit a friend's place for dinner and gotten lost on more than one occasion, you're arguably not as smart as slime mold. Because slime mold, if it follows a path that doesn't lead to food, well, it simply won't go that way again. Now you're probably thinking, it's lecture 23, and Indre has finally lost her mind. But I assure you, slime mold has a type of memory system. As it travels along the forest floor or up a tree or wherever it is that slime mold goes, it leaves a trail of chemical signals. If there's no food at the end of the trail, the signals tell the mold, don't go here, and so it doesn't. Pretty amazing, but it gets even better. In 2012, biologist Chris Reed put slime mold in a maze, the kind often used to test the spatial navigation powers of rodents. Food was down one arm of the maze and not the other. Sure enough, the mold learned which arm held the food and avoided the unrewarding parts of the maze 96 times out of 100. Well, you might be saying to yourself, maybe that's not such a hard task. After all, maybe the mold has some sort of precursor of a nervous system. We evolved out of just tiny organisms ourselves, so maybe this is just a more advanced form. But slime mold has no such central executive. It's made up entirely of individual single-celled organisms. It's a moving clump of individuals, not an organized team of parts. When food is scarce, the individuals gather and form an aggregate that behaves as a single organism. When the weather cools down and food is more abundant, the it separates into a set of theys. The aggregate breaks down and the individual organisms go their separate ways. As such, slime mold is a simple model for the coordination of group behavior. When we want to understand a system as complex as the brain or the stock market, we can start with slime mold to extract some general principles. This area of inquiry has become known as the field of emergence. How might this coordination of group behavior work? Well, it's possible that there's a hierarchy within the mold, that some individuals act as generals, gathering the troops when food is scarce and directing traffic. Then they could coordinate the search for food and dictate the trails that the mold should take. This hierarchy is appealing to us civilized humans because it's much like how a company or some countries work. A centralized authority or government tells us what to do and dictates the path that the company or country will take. So we're likely to assume that there's a similar hierarchy in a complex system like slime mold. Someone must be setting the pace. For many decades, this pacemaker hypothesis was the most popular explanation for the behavior of slime mold aggregates. The generals act as pacemakers and control the troops. But after decades of research, the generals remained elusive. No one could find any individual organisms in the slime mold that seemed to take control. All of the cells in the community seemed to be interchangeable. There were no observable differences between them. For a long time, scientists thought that the generals simply hadn't been found yet. No other rational explanation had been suggested for the organized behavior of the slime mold. Then, an applied mathematician named Lee Siegel began working on the problem with Evelyn Keller, a physicist. Sometimes, problems in one scientific field need to be considered from the point of view of outsiders in order to find a sufficiently creative solution. Keller and Siegel suggested that all the individual single-celled organisms in the mold might be secreting a pheromone, or a type of hormone that triggers a social signal in members of the same species, in response to environmental conditions. When conditions are right, they hypothesized, the individuals secrete more of the pheromone. Then they follow the trails of the pheromone that they come across from other individuals. Eventually, they begin to find each other, clustering in small groups at first and amplifying the pheromone signal. Now the small groups become medium-sized groups and more cells are attracted as the amount of pheromone increases. At some point, the community turns into a large slime mold conglomeration, all without any need for a hierarchy or command center. A rational alternative to the pacemaker hypothesis, and one that physicists and mathematicians found completely plausible. But it took another 10 years for this idea to gain traction in the scientific community because it was such a foreign idea in biology. But now it's a classic case study of bottom-up organization, as opposed to top-down, as would be the case if it was a hierarchy. And once scientists recognized the phenomenon, they began to find it in many places. In the formation of city neighborhoods, ant colonies, swarming behavior of birds and fish, even the human brain. In the next 2 lectures, we're going to explore each of these in turn as they illustrate the insights that we've gleaned from the study of emergence. What is the common element in these complex systems? The building blocks are relatively simple, or even stupid, but they mass together to overcome an obstacle or function as an effective unit without the leadership of a central executive. They display the characteristics of emergence. Low-level rules lead to high-level sophistication, or the rise of complex systems out of relatively simple interactions. In emergence, simple agents together perform complex feats that are impossible for any of the individuals to accomplish on their own. But it's not just the sheer number of simple building blocks that's the key. Without more, the building block's behavior is more likely to be chaotic rather than organized, competitive or counterproductive rather than harmonious. Rather, the interaction between a set of simple rules that govern the behavior of the agents and their large numbers yields a whole that is greater than the sum of its parts. Emergence can come in one of 2 forms: emergent behaviors or emergent structures. Behaviors describe the actions of a group of individuals, such as the swarming of schools of fish or birds or the work of an ant colony. Emergent structures are the actual patterns observed, the layout of a city neighborhood, or the shape of the school of fish, or the ant colony itself. Emergence has certain properties that we're just beginning to understand. By grasping its sometimes counterintuitive principles, we can begin to predict the behavior of complex systems, even systems like the stock market, which seem to defy much of what we expect. For example, emergence appears to reverse entropy, the second law of thermodynamics. Emergent behavior is sometimes described as a spontaneous move towards order rather than away from it. The idea that single-celled organisms like the constituent parts of slime mold come together and behave as an organized unit seems to defy the second law of thermodynamics, which states that systems move towards a state of disorder or chaos rather than order. How can this be? Well, the second law simply states that the total order in the system must decrease, but not where and how. For example, when food is scarce, the slime mold collects individuals, decreasing its entropy. But then the aggregate is more efficient at extracting energy from the forest floor, thereby breaking down molecules and increasing entropy in the ecosystem at large. There are several other properties or rules that emergent behaviors or emergent structures seem to follow. For example, more is different. A few individuals don't seem to show the emergent pattern, but thousands do. It's only by observing the system as a whole that the behavior or the structure comes to light. Also, ignorance is useful. The individual components should be fairly simple and/or stupid. That's why we build computers using the binary system of ones and zeros. If the components are too smart, they might begin to make their own decisions, throwing the system out of whack. Like if your individual neurons decided to branch out on their own. As we'll see, however, there are some times in which this rule doesn't apply. Emergence also depends on or encourages random encounters. Without haphazard interactions, the system might not be able to find new solutions to a problem. A slime mold might not find a path that leads to food. An ant colony might not notice an invader. Another property. There are patterns in the signs that an emergent system's constituent parts exchange with one another. The pheromone trail of the slime mold has a gradient that the aggregate follows. More pheromone means more food. Ants communicate with each other using a limited number of signals. Finally, local information can lead to global wisdom. Slime mold individuals talk to their neighbors, not some central executive, but the result is behavior that helps all of them. With these properties in mind, we're well equipped to delve further into the bizarre world of emergence and see how order rises from chaos. We like to think of humanity as the most successful species on Earth. But there's an argument to be made for the superiority of insects. Certainly, they vastly outnumber us, with more than 350,000 beetle species, only beetles, discovered so far. And that's just one type of insect. They also predate us and undoubtedly will outlast us. In some parts of the world, insects are our biggest competitors for food, claiming about 75% of the available nutrition in parts of Africa, for example, where food for humans is scarce as a result. In the US, we spend billions of dollars fighting off insects from our crops, often spraying deadly chemicals that are just as harmful to us as they are to them. But we also rely on insects, such as bees and flies, to pollinate our crops, and without them, our food supply would be in danger. And then there's the fact that insects kill members of our species every day by spreading disease. But we can still haughtily claim superiority over them in terms of civilized behavior, right? Well, we might be able to speak and read and write, but honeybees can dance their way out of a sticky situation. And ants have a language of chemicals that includes signals for food sources, task assignments, and even a signal indicating it's time to bury a friend. Arguably, insects of the Hymenoptera order, including ants, bees, and wasps, rival the social complexity of humanity. Let's consider ants more closely. It's easy to kill an ant. On its own, the little creature is simple and stupid. But ants live in colonies, some of which contain upwards of 20 million individuals. In fact, ants make up about 30% of the entire biomass in the Amazonian rainforests. That's a remarkable number. And they're not defenseless when they unite. There are at least 5 species of ants that kill many humans every year. Ant colonies are arguably better organized than many of our cities, with strategically placed cemeteries, trash heaps, and even an underground bunker to protect their queen. But the queen moniker is deceptive. Unlike in a human monarchy, she wields little power over her subjects. She can't tell them what to do or organize their activity or even influence their behavior aside from giving birth to new offspring. Instead, she's entirely at the mercy of the colony. A typical ant colony is made up of the queen, who is solely responsible for the reproduction of the colony. That is, every member is her offspring. A large number of sterile worker ants, all of whom are female, and possibly a small number of male and female winged sexual ants. Once in a while, the winged sexuals leave the nest for their nuptial flights, departing en masse to avoid predators, and only when the weather is right. It's odd that they know seemingly intuitively when to go out. They will then reproduce using pheromones as signals, competing with one another so that only the fittest get to actually mate. Then the females will leave with abdomens full of sperm, often with enough to last 20 to 25 years, and they will become queens of their own colonies. The males? They die. Sorry, guys. Ant colonies vary in size, but among the largest are a super colony on the coast of Japan, which is estimated to contain over 300 million worker ants and 1 million queens spread across 2.7 square kilometers. And then there's another one in Melbourne, Australia, measuring 100 kilometers in diameter. But what's really amazing about ants is just how complex and organized a colony can be without a brain or a central leader. And by observing the movements and behaviors of the individuals in a colony, we can begin to understand how the principles of emergence can help the lowly ant achieve great things. Let's take the local information can lead to global wisdom principle and see how it might apply to our ants. Ants think and act locally, but the conglomerate of their actions improves the conditions for the entire colony. Harvester ants, for example, need to bring in enough food for the entire colony, but the size of the colony changes with time. They also need to make sure that there's just enough, but not too much food stored in the nest. So they need to also see that their surrounding area has enough food to bring into the nest and that there aren't any other ant colonies in the vicinity. And they need to dispose of the colony's dead bodies at the maximum distance from any colony entrance. No individual ant is capable of making these assessments and adjusting the colony in response. No ant has a bird's eye view of the entire colony and its surrounding area. But every ant speaks the language of pheromones, 10 or 20 chemical signals that can tell an ant who's on foraging duty, where the food is, whether there's danger, and when it's time to bury a fallen comrade. These chemical signals are on their bodies as well as in the trails that they leave behind as they go about their business. Harvester ants can not only sense the presence of one or more of these chemical signals, but they can also sense the gradient. That is, whether they've bumped into 10 foragers in an hour or 100. By adjusting their behavior based on this knowledge, they can use local encounters to affect the entire colony. Now, ants don't assess the size of the colony, rather, the size of the colony affects the ant's behavior, which is a subtle but important point. We go from a relatively stupid individual to a smart, organized group. Another feature of ant colonies that helps us understand emergence is the fact that although the average lifespan of a colony is about 15 years, individual ants, other than the long-lived queen and the short-lived males, only survive about 12 months. But colonies go through a life cycle, with young colonies showing behaviors that are quite different from those of older colonies. How is this possible if no one other than the queen is around long enough to learn from the past? This characteristic of the ant colony, a global behavior that outlasts any individual local element, is at the heart of the intrigue of emergence. Any given ant might die and another will take its place, but the colony as a whole ages and changes. As journalist Stephen Johnson puts it, it's as though your house, instead of gradually breaking down, sprouted a new, more durable roof after 5 years and a new garage after 10 without your help. The life cycle of harvester ants starts with one queen who digs a little hole and lays her eggs. Once her first set of offspring reach adulthood, they go out and get food. They build a nest, and then the queen lives down in the nest for the next 15 to 20 years. When the colony is about 5 years old, it reaches maturity with about 10,000 individuals, and Thereafter, the population size of the colony stays constant until the colony dies. How does it know that it's reached maturity if no ant other than the queen lives for more than a year and the queen has no control over her offspring? Well, the ant queen's primary interest actually isn't in controlling the size of the colony. It's in ensuring the survival of her own genes. So under certain conditions, such as when there's more than one queen in a colony, she will reproduce less often to conserve energy for the times when she might have to fight and defend her turf. As for the other ants in the colony, remember that the average age of the ants remains static over time. Only the size of the colony changes. So any changes in terms of task allocation or other colony behavior with time must come from somewhere other than the ants themselves. They are not older and wiser. Only the colony itself is. And the rules that they follow don't change. For example, let's say that I'm a forager ant and that one rule is that as long as I meet 3 other foraging ants per second, I will keep calm and carry on. That is, I will keep doing my task no matter what environmental obstacles I encounter. But if the rate of meeting other forager ants is lower, that is, it's less common for me to meet up with other foragers, then I will be more careful when I'm outside the colony. I'll fight with ants from other colonies and protect my turf. But if I meet lots of foragers from my own colony, we'll practice conflict avoidance with ants from other colonies. With this simple rule, younger colonies with fewer ants and older colonies with more ants will behave differently in response to obstacles in the environment or the presence of another rival colony. Younger colonies will fight off ants from neighboring nests. Older colonies will keep the peace. And the colony as a whole will endure. Seems awfully, well, intelligent, doesn't it? It's not just ant colonies, of course, that can teach us about emergent behaviors. One of the most amazing wildlife experiences is to observe swarm behavior. Swarms of insects, schools of fish, flocks of birds, herds of mammals, all moving in one complex, coordinated group. Once again, like slime mold and ant colonies, there's no central organizing force. Rather, the group is made up of relatively simple individuals, all of approximately the same size, who follow a set of rules. From this set of rules emerges a coordination that is not possible from any single individual. Watching a flock of birds is fascinating, but unless you're a keen ornithologist, it's virtually impossible to see the rules that the birds obey. Why don't they bump into each other? How do they know precisely when to turn, how far to climb, how quickly to fly? Applied mathematics has made a huge leap in our understanding of flocking behavior. Back in 1986, a computer programmer named Craig Reynolds created an artificial simulation of birds flocking called Boids. To simulate flocking, Reynolds programmed up simple bird-like objects and instructed them to behave according to 3 rules. First, to steer clear of local flockmates, thereby avoiding crowding. Second, to steer towards the average direction in which local flockmates were heading. And 3, to steer towards the average position or the center of mass of local flockmates. He called these rules separation, alignment, and cohesion, respectively. This very simple framework proved to be remarkably accurate in simulating the flight of a flock of birds. And by extending it to add obstacle avoidance and goals, such as finding food or avoiding predators, the program is nearly perfect. Just like birds, fish that swarm in schools follow simple rules for navigating in a group. Although the ill effects of collisions among them are much less dire, about a quarter of all fish stay together or shoal for their entire lives. Half of all fishes shoal for some part of their lives. Fish often choose shoal mates on the basis of how similar they are to themselves in terms of size and appearance. They also shun unhealthy fish and prefer to shoal with kin. These preferences underscore the adaptability of shoaling and, in fact, help us understand why any animals might prefer to live in swarms. At first, it seems counterintuitive to choose to live in such close proximity to individuals with whom you're competing for food and mates. But there are several advantages to staying with the herd. Arguably, the most established explanation for herd behavior is the selfish herd theory proposed in 1971, which suggests that herd behavior is largely selfish rather than social. The idea is that individuals within a population seek to reduce the risk of being eaten by predators by placing tasty alternatives between themselves and their hunters. Since predators generally attack the closest prey, ensuring that there is a member of your species between you and the predator is a fairly effective way of protecting yourself. Supporting the selfish herd theory is the observation that in most herds, swarms, shoals, and flocks, the fittest individuals, those who are the strongest, occupy the central positions, while the weaker ones remain in the periphery, where the predators are most likely to strike. For example, when faced with prey, fiddler crabs tend to run towards the center of their group rather than simply away from the predator. Other species have also been observed to swarm in response to predation rather than scatter and optimize their distance from predators. In addition to putting an appetizer between you and your hunter, swarming can also be beneficial by confusing predators or overwhelming their senses with stimulation. This predator confusion effect is supported both by observations in the field and computer simulations. Living in large groups also increases the number of eyes available to detect predators or find food. This feature of mass collaboration has been adopted by many businesses, with the idea that two heads are indeed better than one, or that more eyes and more minds will see and therefore solve problems more effectively. What's more, there's a reproductive advantage to shoaling, as finding a potential mate when you're traveling with thousands of potential suitors requires much less energy than building a profile on Match.com. And for birds and fish, grouping together can improve their aero or hydrodynamics, just like bicyclists bike in packs to reduce drag. So, how does shoaling, flocking, or other herd behavior that involves complicated coordination emerge? Taking fish as the example, many young fish have to practice schooling in small groups before they can join a large group. This practicing behavior is instinctive, rather than being taught by their elders. Shoaling species generally have eyes on the sides of their head, and vision seems to be an important sense for schooling behavior, as seeing your neighbor is of critical importance. Many of these species have evolved marks along their bodies or stripes to help individuals get their bearing. And Craig Reynolds' rules of separation, alignment, and cohesion apply just as well to schools of fish as they do to flocks of birds. By observing the behavior of slime mold, ants, birds, fish, and other animals, we can begin to see how order can emerge out of chaos, and how the collective can be smarter or more effective than the individual. The key to understanding emergence, it seems, is to suss out the rules that the individuals follow, a bit like the algorithms behind computer programs that accomplish great feats with a simple binary code of ones and zeros. In fact, ant-based routing, a type of computer model that simulates various scenarios using swarm intelligence, has been used by computer scientist Douglas Lawson to help Southwest Airlines figure out the most efficient way of boarding passengers and of assigning aircraft arrivals to available gates. It turns out that, at least when it comes to gate assignments, letting pilots choose their gates, just like ants choose their foraging paths, is more efficient than using a centralized assignment algorithm. The colony of pilots works better when each one is left to his or her own devices, rather than taking orders from some command center. And to the outside observer, there's no difference. The details and the rules governing complex systems remain far from clear, and their implications are still being explored. Could simple rules governing the behavior of unthinking molecules have generated the complex behavior that is life itself? Could individual neurons acting in response to neurotransmitters, the way ants in a colony respond to pheromones, operate in concert to produce the thinking brain? And could emergence operate on a macro scale as well? In the systems that we've studied so far, the component parts have been fairly simple and predictable. Single-celled creatures, ants, birds, fish. But what happens when those components are as complicated, stubborn, and wily as we are? We'll consider these important questions in our next and final lecture.